Okay. All right. So being lightweight is not only about the size, and it is also about the performance. So we are assuming, of course, it has enough security. So we need to consider the performance. In cryptographic algorithm design, there's a trade-off between performance and resources required for a given security level. For instance, you can add more operations to have a more secure design, but putting more operations result in slower performance, right? So there's a sweet spot that you want to hit where you have the best performance and the best security. So this is one of the aims. But performance in high-end devices, generally we focus on the performance by talking about throughput, like megabits per second or gigabits per second. So we are focusing on how many gigabits you can encrypt in a second. Or of course, if you're implementing for a special device, you are considering cycles per byte. Okay, this is how you provide the performance. But for the lightweight devices, now we have to express the performance in terms such as power, energy consumption, latency, and throughput. And sometimes throughput might be the least important for that kind of a device, on the contrary to the high-end devices. So the resources required for a hardware implementation are usually summarized in gate area, gate equivalents, or logic blocks, also known as configurable logic blocks, logic elements, adaptive logic modules or slices. In software, this is reflected in registers, RAM, and ROM usage. Okay. So resource requirements are sometimes referred to as costs, as adding more gates or memory tends to increase the production cost of a device. So this is actually the main problem we are having with the IoT. So you want to build thousands or millions of devices, but you want to do it in a very cheap way, because even if you increase the building cost by a single cent, if you are going to build a million device, then you use thousands of dollars. So this is why you are trying to make it as cheap as possible. But once you do it, for this reason, people actually remove the security part from the device. This is why many IoT device does not come with built-in security. So this is what actually this competition and the algorithm designs are trying to solve with lightweight cryptography. So let's first look at power and energy consumption. Power and energy consumption are relevant metrics due to the nature of many constrained devices. Power may be of particular importance in devices that harvest power from their surroundings. So these devices don't have their own battery, like smart cards, so they take the energy from the environment. An example would be an RFID chip that uses the electromagnetic field transmitted by a reader to power its internal circuit. Again, we use these devices a lot. So we open the doors of our buildings, or we pay at the cafeteria with our IDs. These are these cards. Also, you can use your credit card as a contactless device to pay the device, and those devices don't have their own battery, so power is important for this kind of devices. And for the credit cards in Turkey, either they are using AES or triple DES, so you have to check which one your credit card uses. Energy consumption, in other words, power consumption over a certain time period, is especially important in battery-operated devices that have a fixed amount of storage energy. So this is important in many scenarios. For instance, if you are using sensors and if they have battery, if their battery does not last long, then you have to charge them or replace the battery from time to time. This is also valid for medical implants, right? So if you perform a surgery and put a device there, you wouldn't want to perform the same surgery once a year and replace the battery, right? It should last very long. So in order to have smaller energy consumption, your algorithm should, perform less amounts of operations and so on. So the batteries in some devices may be difficult or impossible to recharge or replace once deployed, like in the medical implants. It should also be noted that power consumption depends on many factors other than the algorithm use, such as the threshold voltage, the clock frequency, and the technology used for implementation. So with the better nanotechnology, you can build smaller devices, but once the devices get smaller, they consume less energy. This is why we can actually get better GPUs all the time. Because with the nanotechnology, for instance, if with your current nanotechnology, if you can put 1,000 cores on a GPU, at the next generation, you can put 1,000 cores on the half of the device, so you can put 1,000 more cores on the device. Now you end up with 2,000 core GPUs, but the energy consumption becomes somewhat similar to the previous generation, because once you build the cores smaller, they consume less energy. Similar thing applies for these small devices. So, using a better nanotechnology allows you to have devices that consume less energy. So we talk about power and energy, but let's talk about latency. This might be very important in industrial IoT, because latency is especially relevant for certain real-time applications. For example, automotive applications where very fast response times for components such as steering, airbags, or brakes are required. So in modern cars, even the parts of the car communicate with each other. For instance, if something happens to the back of the car, they send a signal to in front, and that kind of communication should be really fast. So by latency in encryption, we mean that it is the time that is required once the plain text is received and converted into a ciphertext. So if you have a very small amount of latency, this means that you encrypt really fast when the plain text is received. So it is different than throughput, because at the throughput, you look at how many megabits or gigabits you transfer in a second. But this is the seconds or microseconds that you need once you receive the plain text and produce the ciphertext. I think here it explains in a better way. Latency can be defined as the measure of time between the initial request of an operation and producing the output, right? So for example, the latency of an encryption operation is the time between the initial request for the encryption of a plain text and the reply that returns the corresponding ciphertext. This is what I was trying to explain, actually. So throughput is somewhat different. Throughput is actually the how big amount of data you can transfer in a second in an encrypted way. So throughput is the rate at which new outputs, for example, authentication text or ciphertext, are produced. Unlike conventional algorithms, high throughput may not be a design goal in lightweight design, because maybe you have a very small sensor and they are maybe transmitting small amounts of data. So you don't need too much throughput, but you need very small amount of latency, maybe because you are performing, your sensors may be recording some data 100 times in a second. So you have to send them in a very fast way so that you receive the data by the aggregator and then perform operations on them. But of course, moderate throughput is still required in most applications. So let's look at now to the hardware-specific metrics. Resource requirements for hardware platforms are typically described in terms of gate area. The area of an implementation depends on the technology and the standard cell library and is measured in nanometer squares most of the time. Array can be stated in terms of logic blocks for the field programmable gate arrays, FPGAs, or gate equivalents for ASIC implementations. So on FPGAs, a logic block is the basic reconfigurable unit that contains a number of lookup tables, LUTs, flip-flops, and multiplexers. And logic blocks are implemented differently on different FPGAs. The number of LUTs, flip-flops, and multiplexers depends on the FPGA family. So this is also one of the problems. Once you have an implementation, an optimized implementation, how many LUTs, flip-flops, and multiplexers you require actually depends on the FPGA that you are going to use. And each family have different architecture. And with new models, sometimes, you can perform less operations and have the same results. So comparing results on different FPGAs is not a good idea. And also comparing, even if they're in the same family, they may be built with different nanotechnologies, so comparing results again is not that easy. So this is one of the problems once we have. So in the competition, they try to, have results on the same device so that they can compare the implementations. The number of input and output bits of the LUTs also depend on the FPGA family. Yeah. So it is very hard to compare implementations. This is one of the main problems. For ASICs, one gate equivalent is equivalent to the area that is required by the two input NAND gates. So this is how they measure the GEs. The area in GEs is obtained by dividing the area in nanometer squares by the area of the NAND gate. The number of gate equivalents of a hardware implementation is therefore very specific to a particular technology. So that is not possible to directly compare the number of gate equivalents of implementations across different technologies. As you can see, same thing also applies here with the FPGAs. So in the FPGA part, we don't know how many LUTs or multiplexer we would need. And in this part, you cannot compare gate equivalents with different technologies, nanotechnologies. A low-cost RFID tag may have a total gate count of between 1,000 to 10,000. So you might say that, okay, if I have 10,000 gates equivalents, I can put many encryption algorithms here. But actually, that 10,000 gates will be used by the smart card for many other operations. So for the security part, for the cryptographic operations, you can only use the 20% of that device. So this is why you generally have 200 gates to 2,000 gates. So implementing AES with less than 2,000 gate equivalents is not that easy. This is why we need lightweight algorithms. This is why actually industry came up with their own algorithms, and those were broken and some disasters happened. So you can actually increase this gate counts, but then to put AES in it, but then the price of the card will be expensive, right? So this is one of the problems. This is why credit card companies have to decide what to do. So they can give you a very expensive card and be secure, but then they have to charge you money to give you that credit card because it will be very costly for the bank. So they have to take some money from you to overcome that problem. But more importantly, I tried to explain this. Area requirements and power consumption can be correlated, in which case minimizing area also tends to reduce the power consumption. So this is a physical property. Actually, this is why I gave an example from the GPUs. So for instance, currently we have GPUs with 10,000 cores, and they consume around 300 watts. Probably in the next version, so currently we have 4,000 series with NVIDIA. So in the 5,000 next year or the following year, probably they will use a better nanotechnology. So we will have maybe 20,000 cores, but this time, instead of 600 watts, maybe they will consume 350 watts or something. So having a smaller area is important. So if you can implement the same algorithm using smaller amount of gates equivalents, then you will have better power consumption. So this was for the hardware part. So let's look at the software specific metrics. For software applications, resource requirements can be measured by the number of registers as well as the number of bytes of RAM and ROM that are required. So people are used to write codes for the CPU. So generally, they don't bother with registers. But if you are familiar with GPU programming, there you have very limited of registers, so you are familiar with how to use them. But for very small devices, now the registers becomes important because you have very small amount of registers. So functions that use a small number of registers have a lower calling overhead, as fewer variables must be placed on the stack before the registers can be overwritten. ROM is used to store the program code and can include fixed data such as S-boxes or hard-coded round keys, while RAM is used to store intermediate values that can be used in computations. So this is why you need to consider how much RAM and ROM you are going to need when you are designing an algorithm. So this can lead to additional trade-offs between calculating values on the fly versus looking up values in the table. So this is actually one of the implementation techniques in cryptography. Sometimes you prefer to do everything on the fly to save the memory. But if you do those operations on the fly, you have to perform a lot of operations, so you lose from CPU cycles, but you save from the memory. So it is a time memory trade-off. And if you have enough memory, you might say that, okay, I can pre-compute these results, put it in a table, store it in the ROM, and then I can use less operations to have the same results. So this time and memory trade-off in the implementations appears all the time, regardless of it is lightweight or not. Even for AES, we focus on different kinds of implementations on the CPU or GPU. Okay.